Welcome to qnawire.
Okay, so temperature that a stationary probe will actually read is the stagnation temperature. So when the velocity is equal to 1 meter per second, we'll have T0 is equal to T plus V squared over 2Cp. We know T0 is the stagnation temperature we're looking for to determine. T is the static temperature, which is given as 320 Kelvin. V here is 1 meter per second, and we know that the specific heat of the air at a constant pressure is 1.005. The reason why I use the specific heat of the air at a constant pressure as 1.005 kilojoule per kilogram times Kelvin is because the static temperature is really close to the room temperature. So therefore, the difference between the actual specific heat of the air at a constant pressure in this case should be not much difference with the specific heat of the air at room temperature. Okay, so we can just use 1.005 kilojoule per kilogram times Kelvin as the specific heat in this case. So now let's plug in back to the equation to determine the stagnation temperature. So stagnation temperature can be equal to 320 Kelvin plus 1 meter per second square. But remember, we need to convert the meter per second square here to kilojoule per kilogram, because the one we are looking for to determine is the temperature, and the temperature has a unit Kelvin. So in order to get Kelvin, we need to use kilojoule per kilogram divided by the specific units, which is kilojoule per kilogram times Kelvin to get Kelvin. So therefore, we need to convert it to kilojoule per kilogram. Because meter per second squared divided by kilojoule per kilogram times Kelvin will give us nothing. Okay, so therefore we need to convert it. And so the conversion between the meter per second to the power 2 and the kilojoule per kilogram is about 1,000. So we have 1 kilojoule per kilogram over 1,000 meters squared per second squared. And then divide by 2Cp, which is 2 times 1.005 kilojoule per kilogram times Kelvin. And this will give us the stagnation temperature is about 320 Kelvin. Okay. The reason why the stagnation temperature and the static temperature is about the same is because the velocity is really small, which means that this process is really close to the adiabatic process. Okay. For the next question, so now the velocity becomes 10 meters per second. So now let's plug in the values. So we have T0 plus V squared over 2Cp, which is 320 Kelvin, plus 1 meter per second square, and then times 1 kilojoule per kilogram over 1,000 meters squared per second square, and then over 2 times 1.005 kilojoule per kilogram times Kelvin, and this will give us the stagnation temperature. This is 10 meters per second here. Okay, and this will give us the temperature is about 320.05 Kelvin. So now let's take a look at the third case. So now the velocity is 100 meters per second. So therefore, this can be equal to 320 Kelvin plus 100 meter per second to the power 2, and then times 1 kilojoule per kilogram over 1,000 meters squared per second square, and then divided by 2 times 1.005 kilojoule per kilogram times Kelvin, and this will give us the stagnation temperature is about 324.975 Kelvin. And then if velocity is equal to 1,000 meters per second, we'll have the stagnation temperature is 320 Kelvin plus 1,000 meter per second to the power 2, and then times 1 kilojoule per kilogram over 1,000 meter square per second square, and then divide by 2 times 1.005 kilojoule per kilogram times Kelvin, and this will give us the temperature is about 817.512 Kelvin. And these are the answers for this question.